day, 10Cs, and welcome to Chapter 5, Relations and Functions. Relations and Functions, an interesting chapter because it builds on a lot of grade 9 material. And what we're looking at with that is how numbers or items are related to each other. Now, we're going to initially look at ways of showing the relationship, but then we're going to get into some new terminology and new ways of presenting the way things are related. So a little bit of review stuff. Seems like it's going to be pretty easy, but then we go a little different. So be prepared for some nice review and then maybe a little bit of thinking as we work through this chapter. So here we go. If we turn to page 2, we can start with the simple definitions of what a relation is. And a relation is a specific association between one group of data and another. So it's just the relationship. What's the association between two groups of data? Now, a set is a collection of distinct objects. So really, if we go back up to our first definition, what we're looking at is the association between one set of data and a second set. So that's what we want. Here's a collection of data. How does it relate to another collection or set of data? And then when we go to element, an element is one piece of a set. So that's what we're looking at. If we wanted to maybe look at some examples, a relation could be as simple as a set of numbers. 4 relates to 8 in some way. It could be majority of people in this class. We could say boy to 15, meaning boy in this class is 15 years old. Not everybody, but it's a relation that in general would work. A set example, well, a collection of distinct objects. Doesn't have to be a number. It could be, but let's just say a set could be the fingers on your hand. That's a set of distinct objects. And an element within that, if I wanted to tie those two together, an element would be your thumb. Because your thumb is one piece from the set of fingers on your hand. So we're going to look and use this terminology a bit in terms of taking elements, creating sets, and then seeing the relation between one set and another. Now, this is what you've seen a lot of this in the past in junior high, is we looked at, back in junior high, the relation and the way things could be related. We looked at the fact that table of values could represent a graph, or a graph could represent a table of values, but those things also come from equations in words. One situation could be explained or shown their association 4 different ways. And the last way, this arrow diagram, is another way to show that relation that we'll look at in a couple minutes. But let's start by looking at example 1 on this page and just see. Here we have a set of ordered pairs that show a relation. What are the 4 ways we've seen in the past of showing that relation between the values? Well, the first thing, remember, ordered pairs are stating the x and y value in that order. Well, the first thing we could do is we could show it as a table of values. Our x value, our y value, ordered pairs can be turned into a table of values because the first relation we have is x value of 1 relates to the 3. X value of 2 relates to the 4, x value of 3 relates to the 5. But we can take that information, because a table of values is really just an ordered pair, we can graph this. Now, I'm not going to pull out a Cartesian grid right now, but I can just do a decent job of eyeballing what this would look like. Well, 0.13 would be at 1, x, 3y. There's my first point. My second point, 2, 4, 2 and 4. So there would be my second point, or my second object. And 3, 5. The third object in this set. There you go. There's the table of values also shown as a graph. So we can show the relation of these in a table of values or a graph. The next way is as an equation. Now the equation, you got to do some mathematical thinking. Equations tell us, in this case, we end up with a y value based on some relation of what's happening to x. So if we go back to our table of values, because I find personally the table of values is a great way to come up with an equation, how are we turning every x value into its y value here? 1 becomes 3, 2 becomes 4, 3 becomes 5. How do all of those change? Well, every x value is being increased by 2. So there's the relation as an equation. As an equation, we can say what's happening. We can see that relation in a table of values. Oh, every x is being increased by 2. And we can then see it on the graph as well, that every x value is going up by 2 or every y value, every y value is 2 more than the x value that it started with. And the last way that we've seen before is in words. Can you write, explain, describe the equation? But don't use the math terminology, oh, y is x plus 2. We see that in the equation. What's happening? The x values are increased by 2 to give the y values. That's how I can say it in words without just translating specifically what's there. Y equals x plus 2. Yeah, that's a no-brainer, but can you put it in words other than just reading the equation? X values are being increased by 2 to equal our y values. So there's relations we've seen before. Taking a set of data, looking at the elements within that set, and showing different ways to relate them. Now the arrow diagram on the next page, a little bit different than what you've seen in the past. It's just another way of showing that each x value gets matched with a y value. So what we need for this example is we need a set of x values. And mathematically, x is what we always start with. Our x becomes y. That in mathematics is what we have, because you'll almost always see most equations are y equals, and it's somehow based on x. So we always want to start with x, and what are the x values we have? Well, here's all of our individual elements that make up the set. We have 3 and 0 and -1 and -5. There's the set that we have with all of the elements within it. Well, that is going to map onto our y. And what are the elements within y? Well, we have the 7, the 4, the 0, the -1. 7, 4, 0, and -1. And what we do then is, like it says, we put arrows in. 3 maps to 7. 0 maps to 4. -1 maps to 0. -5 maps to -1. Arrow diagrams aren't tricky. It's just another way to look at it, but they won't all be exactly this straightforward either. We will at times have some situations where there are maybe multiple arrows going to a particular element or no arrows, and we will have crisscrossing possibly. It's not always going to be quite that straightforward, but that's what we look at. The elements within the set of X, each will map to an element in the set of Y's. Now, take a look at the next set of examples. What's important to understand is it's not just about data in terms of mathematical data. We can see relations for things that aren't just numbers. So if we take a look at this chart here, we have an ant, an eagle, a snake, a turtle, a whale, and it tells us, well, an ant is an insect. Eagle is an avis. Snake is a reptilia. Turtle's reptilia. Whale's mammalia. What's the relation in words? What's happening here? Well, this is telling us that animals belong to a class. That's all it's saying. It's not rocket science, but every animal belongs to a class. Doesn't have to be numeric data. We can write this as an ordered pair. What do we have? We have an ant is related to insect. An ant is an insect. And writing it as an ordered pair is just another way to show the relation. Each of these elements, the snake, is related to reptilia, another element. Turtle is related to reptilia. So we can see there are different ways of presenting the same data. Now, obviously, if we don't have numeric data, we can't show all ways of representing data. We are not, I don't think, going to be able to create a graph if it's not numeric data. We can't come up with an equation if there's no data. But we see, essentially, we had the table of values on that example. We put it into words. So not all methods will allow us to see it, but there are multiple ways to present. Here's our table of values. There's our ordered pairs. And now we can represent it as an arrow diagram. Now this is the interesting one because we have the ant, the eagle, the snake, the turtle, and the whale in that set. All of our objects within the set. Well, our second set has insects, avis, or aves. Sorry, I'm not totally sure which it is. Reptilia, but reptilia happens twice. I don't need to draw it twice. I just need to identify all of the elements within that set, because then I can now show where the relation is. An ant is an insect. An eagle is an avis. Snake is reptilia. Turtle is also reptilia. So I can show it that a snake and a turtle belong to the same object within that set. And a whale is mammalia. So different sets of data can be shown different ways. All right, so now we can go another direction. What about that arrow diagram? What if you wanted to write it as an equation? So y equals. Y is somehow based on x. Well, an arrow diagram can look confusing, but sometimes looking one way doesn't help us. So what's another way we can represent the association, the relation between my set of x elements and y elements? Well, what about a table of values? I can just transfer this to a table of values because a table of values will probably help us come up with an equation. So what do we have? We have negative 3 as an x element, and it's associated with 9. We have the negative 1, which is associated with 1. 0 to 0. 1 to 1. 2 to 4. And then the 3 to 9. So when we have a table of values, I think it's just a little bit more organized way of seeing that particular arrow diagram. And now, do you see, how does x become y? What is y? Where do the y values come? Negative 3 to 9, negative 1 to 1, 0 to 0, 1 to 1, 2 to 4, 3 to 9. How does that happen? Well, play around with the numbers a bit, and x is being squared. Because negative 3 all squared, the x value being squared, negative 3 times negative 3, there's your 9. Negative 1 is being squared. Negative 1 times negative 1 is positive 1. 0 squared, 0. 1 squared, 1 times 1 is 1. 2 times 2 is 4. 3 squared, 3 times 3 is 9. So there's an equation from the arrow diagram, and even though the arrow diagram looks kind of ugly, well, let's just put it into another way of seeing that relation. And that's what we're looking at doing here. Possible. Again, we have here a bar graph. Bar graph gives us information comparing, in this case, what's the relation? What are we comparing here? Well, look at the title. In this case, we're looking at the average travel time to Vancouver in hours from certain towns, and then it tells us how long it takes. So what's the relation in this table? How far from towns to Vancouver? That's the relation that we can see. And it's presented as, in this case, a bar graph. But the bar graph, can we make this connection as a arrow diagram? Well, which data goes essentially in our first set? Which data goes in our second set? We'll talk more about this, but remember x, this is your x-axis. That's what we want to start with, because knowing we have Horseshoe Bay, we have Lillooet, we have Pemberton, we have Squamish, and we have Whistler. There's our first set of data with all the elements. And our y-axis tells us, well, we're going to have information for 0.75 hours. We're going to have information for 4.5 hours. We have information at 2 3/4 hours. We have information at 1.5 hours. And we have information at 2.5 hours. So there's the second set of data, set of elements. And now we can write the arrow diagram. Horseshoe Bay, 3/4 of an hour to Vancouver. Lillooet, 4.5 hours to Vancouver. Pemberton, 2 3/4 hours to Vancouver. Squamish, 1.5 hours to Vancouver. Whistler, 2.5 hours to Vancouver. So there's all kinds of ways that we can present data. So how far from towns to Vancouver? Again, I skipped the table. In this case, we were able to come up with the arrow diagram without too much trouble, but we could still come up with the table. Again, table is x compared to y. We need to know what town we're in before we know the time to Vancouver. That's what we have to know first, x. And again, Horseshoe Bay, 3/4 of an hour. Lillooet, 4.5 hours. Pemberton, 2 3/4 hours. Squamish, 1.5 hours. And Whistler, 2.5 hours. So, all kinds of ways to show these relationships. Now, if we turn to page 5, what we're looking at here is a special type of relation, and that's a function. Because a function is a special relation where x value only can occur once in a set. We can't have multiple x's. Otherwise, it's not considered a function. And we'll see that later in this unit, this chapter, that functions can only have single x values. So if we look at the examples at the bottom of the page, these 4 examples are all functions. Why are they all functions? Because x values occur once and once only. So this first example, the ordered pairs, we have an x value of 2, 4, 6, and 8. Each x is occurring one time. So that would make it a function. If we look at the second example beside that, a horizontal table of values. Well, we look at the x. This first tells us that we have 1 to 2. 1 relates to 2. 2 relates to 4. So we can see that that's the relation occurring, but what's important to make it a function? X is a 1 or a 2 or a 3 or a 4 or a 5. And it's a function because each x only occurs once. Now the 2 underneath, the graphs are a little trickier. But we can think about the x values that come from a particular graph. Remember, the x-axis is our horizontal axis. So if I pick one of the x values on that horizontal axis, let's say I pick x equal to 2. Well, for my graph, when x is 2, x of 2 only happens once on that graph, right there. So x equal to 2 happens once. If x equal to 1, it only happens once. If x equals -3, -3 is an x value, only happens once. We see that each x value only occurs once, so it's a function. Now the next graph, a parabola, a little bit different than a line, but we still see. Pick an x value. If x equals 2, well, if I find where x equals 2 on my graph, I see that we only hit that graph one time. Here's the graph, and there's where x equals 2 hits it, only in one spot. So x equal 2 only occurs once. X equal to 6 on that graph only occurs once. X equal to -4 only occurs once. So again, with each x value only occurring once, we have a function because x can only occur once. Well, if we move to the second set of graphs there that are not functions, why are they not functions? Well, when I look at the first example, my x values, I see that for this relation, we have x equal to 12 occurs twice. And as soon as x happens more than once, it is not a function. Same thing in our horizontal graph here. Well, we see that x equal to 1 occurs twice. X can only happen once if it's a function, so again, not a function. And I move to the graphs. Graphs can be a little trickier. So again, here's the graph or the function that we're looking at. And what's important to understand is that if I choose x equal to 2, well, x equal to 2 occurs here on the graph, but x equal to 2 also occurs here. So we can see that x equal to 2 occurs twice on that graph. So as soon as an x occurs more than once, it's not a function. And in this case, we actually have at x negative 3, x equal to negative 3, we could think of it as an ordered pair. At negative 3, we get 4, and at negative 3, we also get about a negative 4. Negative 3 also happens at negative 4. So negative 3 happens twice. It's not a function. And that exact same idea happens on this last one. At x equal to 6, we hit the graph there, and we hit the graph there. So if I did ordered pairs, when x equals 6, it occurs at 5 for a y value, but x equals 6 also occurs at negative 4 as a y value. Not a function because the x value occurs more than once. So, functions, we're going to work with them a lot, but how do we know if a relation is a function? If the x only occurs once. Now the graph ones can be tricky, but there's really a quick way to figure this out. The quick way to figure this out is a vertical line test. Vertical being up and down. If a vertical line hits the graph twice or more than once, as soon as our vertical line hits the graph more than once, at any point, it's not a function. So if I just want to draw a vertical line, boom. That vertical line tells me that when x is 1.5, it hits at 2 points. So the x 1.5 has 2 values, so it's not a function. Here I can draw all kinds of vertical lines. At x equal to negative 2, I see that it hits the graph twice. So x negative 2 occurs, that x occurs twice, so it's not a function. If I go to this second example, I can draw all kinds of vertical lines that only hit once. So each x here is only occurring one time. But if I can draw a vertical line on any part of the graph and it occurs more than once, it's not a function. Here we see that at x equal to 3, x equal to 3 actually hits the graph 3 times. So it's definitely not a function. And that's a vertical line test. Quick, easy way to figure these ones out. Finish with the last two. We looked at these ones, a parabola. If you draw a vertical line, you will see that that vertical line is only hitting the graph at one point. So each of those x's are only occurring once. So that makes this one a function. And the line graph, honestly, is the easiest one because any vertical line on a line graph, we can see that that x value hits once. This x value hits once. You will not have any double contacts with a linear graph. So anything linear is definitely a function. So all kinds of things to think about. Very quickly, my suggestion, stop the video, give these 6 a try. Is it a function? Yes or no? Then turn the video back on and we'll do it together. So the first one, we have x values of 2, 5, and negative 5. X doesn't occur multiple times. Number 1 is a function. Number 2, we have x equal to 6, 5, and 4. X equals 6, 2 times. So it's not a function. Now, 3 and 4 arrow diagrams, personally, I find it a little tricky to work with arrow diagrams. I prefer ordered pairs. Object 1 relates to 4. Object 2 relates to 1. Object -5 relates to 1, but object -5 also relates to 7. So our x values, we have -5 occurring twice. So this is not a function. -4, well, we have a double arrow, same as number 3. However, if we think ordered pairs, 1 relates to 2. 3 relates to 2. 4 relates to -5. Now we have y's occurring twice, but who cares? A function is dependent on the x's, and each x is occurring once, so that is a function. And then the last two, 5 and 6, easiest way, vertical line test. If I do a perfectly vertical line, not that these are perfect, I see that each vertical line will only hit the graph in one point, which means each x only occurs once, so it is a function. And number 6, well, I see the first line I draw. That x value is occurring twice, so right away when x occurs twice, it is not a function. So a whole bunch of terminology, new terminology, some old terminology. There you go. Please note in the booklet, pages 6B, 6C, 6D, they're labeled as such. After page 6, you will have 3 pages because they've been added to the notes package. You have the textbook, you have the booklet pages, not overly complicated, just different. You need to be familiar with it. Get her done.